Swayam Prabha. Digital India. Educated India.
Hello everyone. So this is the fifth lecture of this week and the last lecture of this week. So in lecture 4, what we have done is this, right? If you recall, we were doing this example, and then finally we had these equations, that this is the final, after assembling, this is the final equations we have. Okay. Now you see, if you remember, then I told you while assembling these, what we did is we had an element level information. These two are essentially the element level information. Element level, this is element level information. And then once we have the element level information, then we have the free body diagram of the each joint, each node, and then apply the equilibrium equations at the free body on the free body diagram of the joints, and finally we had this expressions. Okay. Now, without going through all these, we could have done this assembling in a straightforward way, and I will going to show you that first, and then it will result the same stiffness matrix, and then finally we'll see how to solve these equations. Okay, so let us do that. So our problem was like this. If I once again draw it, this is element number 1, this is element number 2, and this is your node number 1, 2 and 3. Okay, and then for element 1 we have the stiffness matrix for element 1 was Ke, K1 was your K small k1 minus K1, then minus small k1 and K1. Okay, this is small k, this is capital K, and similarly capital 2, this element stiffness matrix was K2 minus K2 minus K2 and then K2. These two matrices are symmetric matrices. Okay. Now, this is we have, and then also if we write it in the form of if we write it in the form of equation. Okay. Before that, now let's see. Now let's see what when we write it for element number 1. Element number 1 we have node number. Element number 1, if we take element number 1, it has node number. This is node and this is node. Node number 1 and node number 2. Similarly, element number 2 we have. Element number 2 we have node number. This is node number 2 and this is node number 3. So when we write this stiffness matrix, it is essentially for element number 1, this is corresponding to node number 1 and this is corresponding to node number 2. And then similarly, first row is corresponding to node number 1 and the second row corresponding to node number 2. Similarly, for element number 2, the first column will be correspond to node number 2, and this is for node number 3. This is for node number 2 and this is for node number 3. So essentially, what is this? This gives you what? This gives you 1 element. It means that if we apply it is a relation between load applied at node number 1 and the displacement at node number 1. And if we take this, this is your for node number 2 and column number 2 and row number 1, it tells you that what it is the relation between the force at node number 1 and the displacement at node number 2. Similarly, if we take this value, this gives you what is the relation between force at node number 2 and displacement at node number 2, and this gives you what is the relation at force at this node number 2 and displacement at node number 3. Now, these are symmetric. It means that if you recall the reciprocal theorem, it tells you that if we apply a force at node number 2 and see the displacement at node number 3 and apply the same force at node number 3, see the displacement at node number 2, they will be similar. So, this gives you what is the relation between the force at node number 2 with the force at node number 3 with the displacement at node number 2. So, this is how we can read the we can interpret the every element of the stiffness matrix. Now, we need to assemble it. Now, in the actual structure, see, element wise, if we see for element number 1, we have just two nodes, node number 1 and node number 2. For element number 2, we have node number 2 and node number 3. Now, if we look at the entire structure, it has 3 nodes, node number 1, node number 2 and node number 3. So, naturally, your size of the stiffness matrix will be 3 by 3, because every node you have 1 degree of freedom. So, what will be the size of the stiffness matrix total? K will be 2. Now, we are doing the assembling part now. So, K will be K for the entire element, that will be 3 by 3 matrices, okay, and this will be 1, 2, 3, and this is 1, 2 and 3, right. So, okay. Now, let us see. So, what will be the contribution for 1, 1? Contribution for 1, 1 will be, this is 1, 1. Here we do not have any 1, 1. So, it will be K 1. What will be the contribution for 1, 2? So, you have 1, 2 here. Here there is no 1, 2. So, this is minus K 1. What will be contribution of 1, 3? There is no 1, 3 in either of this. So, it will be 0. Similarly, what will be 2? What will be 2, 1? 2, 1 will be, this is 2, 1. This will be minus K 1, and what will be 2, 2? 2, 2 will be, here we have 2, 2 is K 1, and here also we have 2, 2, 2, 2, which is K 2. We have to add them. So, this will be K 1 plus K 2, and then what will be 2, 3? 2, 3 will be 2, 3 is minus K 2, minus K 2. Now, 1, 3 will be 0, and then it will be 3, 1 will be 0, and then 3, 2 will be K 2, 3, 2 will be minus K 2, this is minus K 2, and then finally 3, 3 will be K 2. So, this is the stiffness matrix now we have, and you look at when we, in the last class also, we arrived at the same stiffness matrix. Okay. So, this is how we can again assemble directly the stiffness matrix. Okay. Now, so now another important thing, I leave it to you. Please think, when we assemble this stiffness matrix, whether the compatibility at every node we have ensured or not, it is ensured, but you yourself think, and then you can write in the forum. Okay. So, once we have, so finally what we have is, finally this is the expression we have. We need to solve it now. The expression is this. So, expression is K, which is a 3 by 3 matrix, and then we have displacement U1, U2 and U3, and this is F1, F1, F2 and F3. Okay. So, this is the final equation we have. Now, we need to solve this equation. Okay. Let us do that now. So, you see, we have this now. in this equation, let us see what are the information we have now. Okay, now look at this diagram. Our actual problem was this, if you recall. Actual problem was this is, and yes, so this is node number, this is your node number 1, node number 2 and node number 3. Okay, let us not write the elements now because we have already obtained the global stiffness matrix. Okay, and what are these so at node number 1 we have here we have U1 and F1. At node number 2, U2 and F2. At node number 3 we have U3 and F3. Okay, now what information we have now? Suppose the problem here is like this. This is our problem. And suppose I have some force, say P4. This is the problem. Okay. Okay. Now from this problem, so this is the actual problem. This is the finite element discretization of the actual problem. Now what information we have? Now from this, and if we map these two, we have these information. See straight. This is node number. Anyway, let us write the node number. This is node number 1, node number 2, and node number 3. Node number 3. So from this, if we map, we know that U3 will be 0. That is straightforward, right? U3 will be 0 because this is fixed end. We don't know what is the value of U1 and U2. U1 need to be determined, and U2 that also needs to be determined. So U1, U2 we don't know. Any other information about the forces? Yes, if you map it, so you will see that F1 is equal to P. The external force here is equal to P. There is no external force F2 at second node, so F2 will be 0. And then F3 is essentially what? There will be a reaction here. There will be a reaction here R, and F3 will be that reaction R. Okay. Now we need to determine these three things. We need to determine U1, U2, and R. So there are three unknown. The equations we have, if you recall. These equations we have three equations, 3 by 3 matrix. K is a 3 by 3 matrix, so this gives you three equations, and then we have three unknown. So we need to solve them, right? Now, so let us write this equation once again. So we had something like this. So this is K1 minus K1 and 0. Again, this is minus K1. This is K1 plus K2, this is minus K2, this is 0, minus K2, and then K2. This is the stiffness matrix, and then this is U1, U2, U3, and then is equal to, this gives you that F1, F2, F3, F1, F2, F3. Okay. Now what we know is F1 is equal to P, F2 is equal to 0, and F3 is equal to R. So this we know, right? So let us F2 and F3, F1. So let us write F1 is equal to P, and then F2 is equal to 0, and F3 is equal to R. Okay. See, what essentially we are doing is, once we have this equation, and then we are providing now the constraint in the sense that, you see, if you try to solve these equations, you can try yourself. Now you have this equation. Okay, if you try to solve this equation, you cannot do that. One property of this stiffness matrix is symmetric. Absolutely fine. You try to invert this stiffness matrix, try to solve this equation as it is without giving any constraint, and then see whether you can solve these equations or not. And you will see that you cannot solve this equation because this stiffness matrix won't be invertible. Now, which is if I try to map that with a real system, in a real system, you see, if you allow all degrees of freedom, suppose there is no constraint in this problem. Constraint means u3 is equal to 0, that is our constraint, right? Now, if there is no constraint in this problem, then what will happen? The problem will be unstable, right? You cannot, so to stabilize it, to make it stable, we need to provide a constraint. We cannot allow all degrees of freedom in a system, right? So that constraint need to be given. These equations are essentially a representation of a physical process. So what you see in the physics, what you see in the physical process, that should get reflected in your equation. And what is getting reflected in the equation, that gives you what is happening physically. So this has to be maintained, and that's why you remember, again I will bring the word called approximation. Your approximation should be such that it is as close representation as possible to the physical system. So what is happening in the physical system, that should get reflected in your equation, and what you observe in your equation, that should be a representation of some physical manifestation. Okay, that is important. So if you do not provide a constraint here, your system is unstable, and if you try to solve this equation without providing a constraint, you will see that you cannot solve this equation. So these two are related with each other. So in order to make it stable, we have to provide a constraint, means here the constraint is u3 is equal to 0, and similarly in these equations, if you have to solve it, getting a solution, you need to provide a constraint, and the constraint is u3 is equal to 0 in this case. Okay, now so let us make u3 is equal to 0. u3 is equal to 0. Okay. Now another important point I want to make is, you see, this is the equation now we have on our screen. Is a pretty simple and very easy thing. But we won't be having similar the problems that we'll be solving in the subsequent lecture. Equations will not be that easy. We need to use a computer to solve these equations. So there, how you apply the boundary conditions, how you apply the constraint, there are several methods, several ways you can apply the boundary conditions. So we will discuss those when we actually talk about implementations, but here let us not go into that. We'll apply the boundary condition in a very straightforward way, but there are other ways as well through which you can apply the boundary condition. We will see that in our subsequent discussion. So now what we can do is this. So all the information now we have provided. We have three unknown now, and these three unknowns are u1, u2 and r. Now what we do is, now we will partition this matrix. Partition this matrix means like this. Let us partition based on what information we have and what information we do not have. Okay. Now let us partition this matrix here. Here the partition is easy because only the third degrees of freedom are known. So partition will be only third row and third column. Had it been like this, that we know what is the value constraint at second node, but the unknown at the first and third node unknown are u1 and u3, that need to be determined. Then your partition, we need to slightly reorient the rows and columns for this partitioning. Okay, the point here is you need to partition based on what information you have and what information you do not have. So u1 and u2 are the unknown, and then u3 are known. Okay, so this is now partitioning. Okay. Okay, now from this what we can do, this gives you, you see, if you take this part only, if you take only this part, let us, if you use only this part, only this part, only this part, and only this part. If you use this equation, then this essentially gives you k1 minus k1 and then minus k1 and k1 plus k2 u1 u2 that is equal to P and 0. This is also stiffness matrix of our subsystem, where after applying the you have made a point that U3 will be 0, therefore the expression, the effect of this part will be 0. The effect of this part will be 0 because U3 is equal to 0. So if you multiply this, it will be 0, right? So if you okay, let us write this, and then probably will be, so it will be this, and plus okay, plus then your 0 minus K2 into 0, that will be equal to P and 0. So effect of this will be 0, that's why we didn't write it. Okay, this will be 0. Okay. Now you look at, so essentially what equations we have now? Equations we have is this. You remove it, we have this equation. Now in this equation you see this is also stiffness matrix of a subsystem. The stiffness matrix is invertible. You please try yourself the entire system matrix, trying to invert it and then see whether it is invertible. Now you get the solution or not. But now just by looking at this, we can say that for all non-zero values of K1 and K2, this stiffness matrix is invertible. Now if we solve it, let us clear some space here. So this will be P and 0. So if we solve it, this gives us, okay, so I'm not writing the solution. So this is, if we solve it, your solution will be something like this. U1, you will get, U1 will be your 1 by K1 plus 1 by K2 into P. This will be U1, and U2 will be P by K2. This will be the solution of U. Now this solution, to get this solution, you really do not need finite element method or matrix method or structural analysis and so on. By simple the idea of your mechanics that you had in your +2 level, you can get the solution, right? But again, the point here is not to get a solution of this problem. As far as getting a solution of this problem, our +2 mechanics knowledge is more than enough. Okay, you don't need all this matrix method, finite element and all these things. But then here objective has not been to get this solution. Objective here is to understand the procedure, understand the steps we follow in these methods. Okay, so this is how we can determine the displacement. Now once we have determined the displacement, we need to find out the reaction, the last unknown, which is R. Now the last equation will give you that, this part will give you that, this part will give you that. Okay, so the first two part gave us this U1 and U2, and the third part will give you that. And if you write it, your expression will be something like this. So it will be from this we'll get 0 into U1, then minus K2 into U2, and then plus K2 into 0, that will be equal to R. So finally, and then you already know U2 is equal to P by K2. If you substitute P by K2 here, we will get R is equal to minus P. So this is another solution. So this is your complete solution. U1, U2 is equal to this, and R is equal to this. By simple spring analogy, you can find out this solution. Okay, so this is how we can apply the solution. Now, before we close, there are few points. Let us just let me re-emphasize, and probably those points will be a continuation or transition from what we have done so far, and what we'll be doing in the next week. You see, we have now understood what is the basic, at least little bit comprehension we have now about what is the philosophy of finite element method. The philosophy is, we have a system, divide the system into small subsystems or small subdomains, write the equations for each subdomain, get the element level information. Those subdomains are called elements, okay. Get the element level information, and then once we have the element level information, add them or assemble them to get the information about the entire system, and then finally solve it. This is the idea of basic philosophy of finite element method. As for the elements are concerned, there are different kinds of elements, different shapes are elements, but shapes alone do not give you shapes do not give you a complete idea about the element. Shapes, along with what are the degrees of freedom at various nodes of the element, are the complete information. Okay, so then most important part in this process is, see, as far as the element discretization is concerned, dividing the entire domain into subdomains or the mesh generation is concerned, that itself is a different branch in altogether, and there are very sophisticated algorithms available for that discretization. So in finite element course, we will not talk about the discretization how to discretize, what are the algorithms to discretize it. See, for this problem we could do it manually, but for the problems that we'll be dealing with, it cannot be done manually. It has to be, there should be some algorithm through which that algorithm translated in a code, and that code needs to be used for discretization. So those aspects will not talk in this course, but yes, one aspect we will discuss when we do the implementation, the numbering of the nodes. In this example, again, it was very straightforward. Either you number in from left to right or right to left, but for arbitrary domain, we have on a 2-dimensional, 3-dimensional domain, how this element numbering is important. Element numbering is important because it will actually gives you how the stiffness matrix eventually look like. Okay, we'll discuss that. So as far as the discretization aspect is concerned, we'll only discuss the numbering system. What is the effect of numbering and how to choose the numbering of this of different nodes. This is one aspect we'll discuss. And then majority of the course, most of the course will be focused to discuss how to get that element level information, and then for different problems. For all the problems, that element level information has to be done based on the governing equations, based on the partial governing equation which represent the physical process. Okay, but in this first week, for some simple system, this element level information can be obtained directly, and that's why we have done it. Okay, now then the theory part of your course will be focused to discuss how to get that element level information. Okay, now there comes another part of the course is the implementation. Implementation will talk about, once you know how to get that element level information theoretically, then we'll apply that, we'll see, we'll apply this to some example problems, and then write the element level information, and then assemble those element level information, and then finally apply the boundary condition. We will see what are the different methods we can use to apply boundary conditions, and then finally get the solution. And we'll also spend some time, little bit time towards the end of this course on processing of this. Once you know this information or the displacement, then how to with this information, say U1, U2 and R, how to get the overall information about the structure, how to visualize it, little bit discussion on that as well we will make. So with this, let us stop, let us finish first week. So next week, next week will be taken by Professor Banerjee. I will probably come again, probably in the 6th week. So till then, bye and see you soon.